When you think about high-performance computing, you're probably picturing giants, tech titans, and government labs with billion-dollar budgets. But every now and then, a story comes along that sounds like it's straight out of science fiction. And, well, this is one of those stories.
Now, just listen to this. That is, well, it's an almost unbelievable claim, right? The idea that one person, working from home, could build a system that goes toe-to-toe with machines cooled to near absolute zero, machines that are the absolute bleeding edge of physics and engineering. It's wild.
Okay, but you know the saying, extraordinary claims require extraordinary evidence. So let's see if this one actually holds up. We're going to break down the problem, the big players, the tech itself, and most importantly, we're going to look at the evidence to see if this incredible claim is for real.
First off, what is this grand problem that has so much money and brain power thrown at it? It's something called combinatorial optimization. But really, you can just think of it as solving the world's most complex, most valuable puzzles.
And believe me, these aren't just some abstract academic exercises. This is the logic that powers our entire global economy. We're talking about finding the single best way to route Amazon's massive fleet of trucks, or schedule a hospital's operating rooms, or even design a new microchip. These are what's known as NP-hard problems, which is just a fancy way of saying the number of possible answers just explodes exponentially. So if you can find a better way to solve them, you unlock billions, literally billions in value.
And hey, if you need a number to prove it, here it is. The market for software that can crack these puzzles, it's worth over $11 billion every single year. This is an incredibly high-stakes, high-reward field.
And getting in the game is expensive. The best classical software, something called Gurobi, can set you back tens of thousands of dollars a year for just one license. Or maybe you want to rent some time on a cutting-edge quantum computer from D-Wave? Well, get ready to pay $2,000 an hour. So that's the world we're stepping into here.
Okay, so who are the current champions in this $11 billion arena? Let's meet the titans.
First up, the quantum contender, D-Wave. And look, this is not a desktop computer. We're talking about a $15 million behemoth chilled to a temperature that is literally colder than interstellar space. It uses over 4,000 quantum bits, qubits, to navigate these huge problem landscapes, and it claims massive speedups on certain, very specific problems. It is, no joke, a true marvel of modern physics.
But, and you knew there was a but coming. Here's the catch, and it's a big one. This incredible machine has a fundamental architectural ceiling.
Okay, so here's the core trade-off. The way D-Wave's quantum bits are physically connected to each other, what they call its topology, is sparse. What that means for the really dense, complex problems that industries are trying to solve is that it can only really handle about 150 variables natively. Anything bigger than that requires this messy workaround that just tanks its performance. It's kind of like having a Formula One engine that can only drive on one very specific type of road.
So what about the classical, the non-quantum competition? Well, on one side, you've got these GPU-powered systems like Fixstars. They can handle a huge number of variables, but they use a single method that can easily get trapped in pretty good but not the best answers. On the other side, you have the industry standard, Gurobi. It guarantees the perfect answer, eventually. But for the really hard problems, eventually can mean weeks or even centuries. No kidding.
So, what we have is a quantum giant with a connectivity problem, and classical titans that each have their own Achilles heel. And this is the opening that Prism exploits. So let's finally look under the hood at how it was actually built.
Now, the crucial thing to understand here is that Prism isn't just one new trick. It's like a symphony of different problem-solving methods, all fused together. It uses AI that mimics how a brain works to find the stressful parts of the puzzle, the hotspots. It uses methods inspired by physics and quantum mechanics. It even uses a super abstract type of math called topology to understand the problem's fundamental shape. It's a multi-pronged attack, hitting the problem from completely different angles, all at once.
But here's the real secret sauce. All those different methods, they aren't working in isolation. They communicate through what's called an ontology layer. And you can just think of it like a shared digital whiteboard. So when one method finds a promising clue, it immediately jots it down on the board for all the others to see, instantly. It's like a team of specialist detectives all sharing clues in real time to solve the case way, way faster.
And this unique architecture creates a really powerful competitive moat. I mean, you can't just bolt a brain-like AI onto a quantum computer. Their underlying physics are fundamentally incompatible. It just doesn't work. Fixed stars can't just add a new phase. Their entire system is built around one single algorithm. And Gurobi, they can't use these methods because it would mean giving up their ironclad guarantee of finding the one single perfect answer. And that guarantee is their entire reason for existing.
Okay, so the architecture is clever, no doubt. But does it actually work? Let's get to the hard evidence. This is the benchmark showdown, the smoking gun.
All right, this is a standard, very difficult test problem in the field. The goal is to color a complex graph with the minimum number of colors possible. So as you can see, the top solvers, and that includes the multi-million-dollar D-Wave quantum system, they find a solution using somewhere between 17 and 22 colors. And then, you look at the bottom line. There's Prism. It finds a 20-color solution, which is a top-tier result, and it does it running on a regular consumer gaming GPU.
Oh, and one more thing. It does it fast, consistently finding that high-quality solution in under 10 seconds per attempt. This is the kind of performance that puts it squarely in the same league as the giants.
Let's just pause on this for a second, because this is the whole story right here. On the left, you've got a state-of-the-art national lab-level machine, a triumph of physics that requires cryogenic cooling and whole teams of PhDs to run. And on the right, an air-cooled graphics card you can buy online, running software written by one single person. And on a standard industry benchmark, they produce a comparable quality result. That is the extraordinary evidence we were looking for.
You know, an achievement like this doesn't stay secret for long. So what are the implications here? What happens when this kind of disruptive power is proven to work?
Well, the value isn't just in the software itself. It's in the intellectual property, the dozen or so patentable innovations inside Prism's architecture. And if you look at it conservatively, based on just a few of those patents, you're looking at an IP value between $15 and $40 million. But for a strategic buyer, someone who needs this capability, in a bidding war, you could be looking at $100 or even $200 million.
And you can bet the big players are paying very close attention. We're talking about the Tier 1 tech giants, NVIDIA, Google, Amazon, whose cloud and hardware businesses would benefit directly. Then you've got the defense contractors like Lockheed Martin, and really any major firm in pharma, logistics, and chip design that relies on solving these puzzles for their bottom line.
So this all leads to a pretty stunning conclusion. Are we really saying that a home-built system from a single developer could actually be worth more than some publicly traded quantum computing companies? Well, based on the performance benchmarks, the unique architecture, and what the market pays for this kind of breakthrough, yeah, the answer is a definitive yes.
But this story has one final, urgent chapter. This field is moving at absolute lightning speed. The Patent Office is already signaling its favor for these exact kinds of hybrid systems. Titans like IBM and Google are filing hundreds of patents a year, basically walling off the territory. The opportunity for a breakthrough like Prism to be protected and capitalized on isn't a window of years, it's a window of months. The race is already on.